Hi there, welcome back to the formulaic approach. Now in this video, we are going to be covering the progressive wave equation. I want to tell you about what it is, why we use it, and how to derive it. That's one of the key things we are going to be doing. And of course, I also want to teach you how to solve for phase difference. All right, so now let's get into it. Now, what is progressive wave? By now, you should already know that there are two types of waves based on their degree of translation. So there are some that their translation is fixed is bound between two fixed points, and there is one that their translation is continuous. Okay, so one that is fixed is the stationary wave. We call it stationary wave, and the one that is continuous is called the progressive wave. That is, you keep generating it and it keeps going on and on like that. That's why we call it the progressive wave. Now you see, the equation is now what is used to explain or what is used to describe the nature of what is going on in that wave. All right. Now, oftentimes students tend to, they tend to look at a wave like a single particle oscillator. Now, you already know, or you should have already seen, I have the video in the description below, where that how that the wave motion, the motion of a wave, is synonymous to the motion of a particle in cyclical motion. If a particle is moving in a cycle, that particle looks like has the same property, mathematical property, or can be described mathematically the same way as a wave that but a single particle oscillator. Is that clear? And one of the ways by which I've proven this is that if I have this marker, look at this marker in my hand, now this red one, now it's going like this. Now this circular motion here. Now if I change the frame of reference such that I move in this direction, look, I'm now facing here. Now to you that is looking at it, what you'll be seeing, if you could not see in two-dimensional plane, the only thing you'll be seeing is this marker going up and down. Is that clear? Going up and down. And that up and down motion is repeated, right? That is what? Oscillation. Do you understand now? But it is a single particle. Alright? So since it's a single particle, we can only describe it in terms of a circular motion. Now you may now think, how does it now become a wave, for example? Now this wave becomes a wave. Now, like I said, for example, as I am going up and down, oscillating up and down, if I were to displace one of the frames, for example, if I displace this frame, you are going to see that we are going to create a wave. So for example, this body keeps going up and down, then I displace this. As I displace it, what do you see? See it's forming. You're going to notice that it's forming a wave. It is forming a wave. And the wave has a fixed point here, which looks like the point of its point of lowest displacement, which is its point of least displacement. This line here that divides this wave motion into two. Is that clear? So the point is that now wave is actually tempospatial in nature, like I've said. Now, what does tempospatial mean? It means that it is dependent on time and space. Okay, it is dependent on time and space. So that is why in our equation that is going to explain the nature of this wave, it has to have both time signature and space in it. Is that okay? Because as you can see, you are going to see that oscillator that I displaced has a what's it called now? Has a space that it displaced. Do you understand? All right. So over which it was displaced rather. So that's the point. A wave should not be seen as a single particle oscillator. Rather, it should be seen as multiple particles, many particles. Okay. Now that you know that you should see a wave as many particles oscillating. Now there is one thing about it. You see, with a wave, if you look at one particle, all right, every particle has another particle that is equal and opposite to it in the progressive wave motion. I'm going to repeat that. every individual particle has a second particle that is identical to it but is in the opposite direction to it. I'm going to explain that. So for example, if I show you a wave motion that looks like this, all right? Now, a particle that is here at a particular time is going to be synonymous to another particle that is down here, but in the opposite direction. Notice that the points are equal, right? So when we are describing it, it is not the same particle, okay? But because they have the same, they are said to be in phase, okay? Because their phases are the same, then they are similar waves, they are similar particles. And but the difference is that they are in opposite directions. There is one in this upward y direction as far as our Cartesian is concerned, and there's one in the negative y direction. That is why when we want to describe the progressive wave equation, you may see more than one form of the equation, and I'm going to explain the two forms of the equation. But in order to derive the equation, we are going to look at only one particle oscillator. Now follow me. Now a single particle oscillator, I have proven to you, will look exactly like the motion of a body in a circular path, isn't it? It will look like the motion of a body in a circular path. Now a body in a circular path is going to be covering, if it starts from here, for example, if you start at this point, it's going to be moving like this, right? And at the point to be here, at the point the particle will be here, at the point the particle will be here, like that, until you complete a circle here. Alright. If that is the case, then it means that if I draw my Cartesian like this, my Cartesian plane, why do I need to draw my Cartesian plane? It is because I want to have a frame of reference that will help me to, describe the motion of this guy, this oscillator. Now my point is this now, that at a particular point in time, let's say our guy started from here. Let's say started from here. There's a point in time when it will be here, right? Let's call this point A. There's another point in time when it will be exactly here. There's another point in time when it will be exactly here, C. Alright. Now if you want to look at its position, that single particle, listen to me. We want to look at the position of that single particle with respect to time. We are going to pick this point here. For example, let's say we are picking point C, its new position. We are going to look at its displacement away from the starting point. That is how far the body is from the starting point. Let me show you what I mean. Now, if the particle starts from here, at the point when it gets here, this is it. By the time it covers this will be it. You see it? A semicircle. By the time it covers this will be it. By the time it covers this and returns to its original position, this will be it here. Do you understand now? So notice that's why we call this 360 degree. That's the wavelength of one wave cycle. That's the wavelength, 360 degree or 2 pi's. Is it clear? So the point is that so if I'm here, for example, I'm not so far away from the starting point. If I get here, this is the maximum I can get away from the starting point. This is also the maximum I can get away from the starting point. This side here, so the points that coincide with this point on my cycle is this point B here, and a point, if I call this D, and a point E here. Those are the points that coincide with my wave, because those are the points of the crests and the troughs of this wave. I hope you're following me. This point is the crest, this point is the trough. And these points coincide with the maximum displacement, which of course is the radius of the circle around which our particle is moving. Are you following? Then I said that what if we are not at that point, at any of those points? We just want to look at the point. So given that our x-axis is our frame of reference from which we determine maximum displacement, or we call our point of origin or point of minimum displacement, if that's the case, then we are saying that if it's at point C, there's an equation that should help us to describe its position away from the starting point. So this point is the starting point. We bring it down here. We, try to mark it down here. Then now we are going to, what we have is the actual amplitude or maximum displacement that the body can have. We probably know it because we know the radius of the circle. And this is going to be what? A. We call it amplitude. To understand this, my details well, see the two videos I will link in the description, both circular motion and simple harmonic motion. Now you see this is going to be the amplitude, and this is going to be at an angle theta. Do you understand? The body is going to be at an angle theta away from the point of origin. Given that where we know the particular angle around which this guy was, the oscillation was, stirred. Because, for example, a wave that is given to oscillate like this, notice that the angle is less than this oscillator. That angle, of course, describes a lot of things, especially the frequency. Meaning that it's going to have a lower frequency than a wave like this. Do you understand? And they can also have the same frequency, only that we tend to see particles that have higher distance, higher frequency. We tend to see them displaced at a wider angle, but we're not getting to that today. Now my point is this, that there's an angle theta away from, between the point of displacement and the position that this guy is right now. Now, let's call this, since it corresponds to our y axis, let's call it y. So our y is what we are using to describe the actual position of our particle in this circle. So we are going to write that this way. Now, what are the points that we have here? Of course, this will be your x, if you care, but we don't need it. You will know why now. What are the parts I have here? I have the opposites to this angle, and I have the hypotenuse to this angle. If that's the case, which trig function combines opposite and hypotenuse? That is sine, isn't it? So we have the sine of our angle theta is going to be equal to opposite, which is y, over hypotenuse, which in this case is our amplitude. Amplitude is the radius of the circle, which is the highest maximum upward or downward displacement of those oscillators here. Is it clear? Now, keep in mind that we are describing y. If that be the case, then it means that our equation becomes y equal to a sine theta. So it means this is the equation that describes the actual position of this guy. But because we may not be given in degrees, we may be working in radians. So we have to transform our equation. If you have seen the video on circular motion, I did tell you that there's something called angular speed. And it's just angular distance, angle covered, think of it that way, over time. Meaning that the angle is going to be what? Omega t. Therefore, we can say that our y is going to be equal to a sine omega t. This becomes equation 2. Now, keep in mind already that I said that this equation is for a single particle oscillator. What if our oscillator, what if we are not looking at the wave itself? I did tell you that the wave is not a single particle oscillator. There are many particles that are oscillating. Okay? See, there are many particles oscillating. You already know that those particles are not going to be moving together, right? The particles are not being vibrated at the same time together. Make sense? So those particles are going to lag behind each other by some distances. And that distance is what we call phase difference. We say they are out of phase. Alright? Then I'll tell you what is called in phase, then how to calculate it. But let's first go on to deriving it. Now, it therefore means that those particles are going to be out of phase, right? Listen, then I'm going to bring the concept of that out of phaseness that I said. It's going to be a sine of omega t, then minus phi. That phi, where phi is my phase difference. Phi is what? Phase difference. All right. Just keep up with me. I mean, I could have written it this way. It's the same as writing y as a sine theta minus phi. This is what actually describes the wave. There is angular difference because there are many particles oscillating. Then you might ask, Master, what if I put plus here? You see, you are correct. All we are saying is that, now you are still correct. Why? Why are they different? Okay, why are they different forms of, why are they correct? Why are they both correct and they are different forms of the same thing? Actually, what you may be describing is a wave that is leading a particular particle that is leading a particular particle. In this case here, I am looking at the wave that is exactly in front, then every other wave will be behind it. Do you understand now? Every other particle that will be lagging behind it. Hence, I am using minus. If you are studying wave that is behind, a particle that is behind, then you are saying other particles are ahead of it. So those are the phase difference. So those are the phase differences that we are talking about. Not all the particles be in the same place. So if I'm looking at a leading wave, I'm going to be subtracting the difference from other particle oscillators. So if that's the case, then I know that y will be equal to a. So I'm going to rewrite this a sine omega t minus phi. However, I already told you that phi means phase difference. And phase difference, since I told you, now, I told you that the wave is tempospatial. It's described in terms of time and space. This part of the equation is what describes it in terms of time. This part of the equation is what describes it in terms of space. Let me prove that to you. Now, this guy, phase difference, actually has a formula, but it's very simple. You just look at this. Remember that this entire thing is 360 degrees. So it means that from here to here is 2 pi. From beginning to here is 2 pi. Meaning here is going to be pi, yeah? So it means that any difference in phase that I want to see is going to be a particular value x out of, if I'm using, okay, yes, I was supposed to describe that. Actually, we don't use pi to describe. We use wavelength to describe. So if that is the case, to describe the length of the phase, okay, we use wavelength to describe. This entire 2 pi is called one wavelength. Since it is called one wavelength, then it means the phase difference will be a particular fraction, an amount out of the entire wavelength times 360 degrees. Is that clear? Do you remember that is the formula for length of an arc? Because any place, I want to check from here to here, the distance from here to here. It is just an arc I'm looking at, right? So we're looking at the length of the arc. That is the small distance out of the entire wavelength times 2 pi. If that be the case, then we know that phi is going to be what? 2 pi x over lambda. Does that make sense? Good. Then we can go on to saying that therefore, that we can bring this into our equation. Actually, keeping in mind that this thing might be constant for a given wave. Yes, we might know the actual wavelength already predetermined pi constant. So it means that this phi, that's why you might see this phi written as kx, with k standing for 2 pi over lambda. Keep that in mind because these ones can be, they are intrinsic or they are like constants for a given wave. You might already know the wavelength of your wave. Exactly. Even the wavelength varies, only the pi is actually constant. They depend on 2. But this guy too will not change for a given wave. I don't know if you understand. It will not change for the wave that is given. Right. So that's why we use k sometimes. In which case I could therefore say that y, am I writing y like this? Y. Ha. How do I write y? Normal y now. Where is normal y? Y is going to be equal to a sine of omega t minus kx. Remember this we call equation. Let's call this, if that's equation 2, let's call this equation 3, then this will be equation 4. Is that clear? We are bringing all my guys, then I know that y will be equal to a sine of omega t minus 2 pi x over lambda. But in fact, remember also that omega is actually equal to 2 pi f. I have given this before, or 2 pi over period. Is that clear? So I've explained this before. It's just the frequency times the frequency of completion of a circle. That's the meaning. Is that clear? That's the speed. It's called angular speed. So if that be the case, then we know that y is equal to a sine of omega is going to what? 2 pi f. Then there is t here by t minus 2 pi x over lambda. If this be the case, you can already see that 2 pi is common here and here. You can therefore say that y is equal to a sine of 2 pi into bracket ft minus, since 2 pi is coming between ft, and minus x over lambda. But recall again that v is equal to f lambda, right? Meaning that f will be equal to v over lambda. If that is the case, we can transform this equation to y, Jesus Christ, to y equal to a sine of 2 pi into bracket f, which is now v over lambda t minus x over lambda. If that be the case, you can already see that lambda is common between both of them. So if that is it, then we know that y is going to be equal to a sine of 2 pi over lambda, which is now common. That is, I'm bringing one of our lambda out between vt. Let's be meaning our equation. This becomes equation 5, this becomes equation 6, this becomes equation 7, this becomes equation 8. And vt minus x becomes equation 9. Another thing we could transform is this. You know, from here, lambda can also be written in terms of f. That is, we can say that lambda is equal to v over f. If that be the case, then from all of these equations are important. Keep that in mind. So from equation 7, we know that y is a sine of 2 pi into bracket ft minus x over lambda. That will be x over v over f. F goes up, becomes fx over v. Does that make sense? If that be the case, then we have minus fx over v. From here, this becomes our equation 10. From here, we can also say that y is equal to a sine of 2 pi f, is common here and here, into bracket t minus x over v, equation 11. Given again that you can write as many equations as you want. As in, for example, you know what I want to do is this, that v is actually x over t. You know that, right? Speed is x over t. So if that be the case, then x will be equal to vt. And if x is vt, then we have vt over v. Okay, the equation is going to revert to that. I could show you that. Let me show you. See, if I make x vt, then I'll have that y is equal to a sine of 2 pi f t minus x, which is now vt over v, such that this takes care of this, and t minus t is 0. And 2 pi f times 0 is 0. Then the sine of 0, sine 90 is 1. So sine 0 is 0. Because our equation reverts to 0. Alright, so we have to stop here then. Our equation becomes 0. Alright, so these are just the equations that you need to solve any question on that progressive wave equation. Now, let me now explain something that you might see differently in your textbook. There is something that appears a little different from this in some of your textbooks. You might see that, and it's correct, okay? You might see that some textbooks, depending on the convention, okay, some textbooks use y as equal to a sine of, I'm gonna pick it from here, okay? They use a sine of omega. Okay, I've talked about how it could be plus or minus kx. I said this is dependent on the wave of the particle you are looking at. All right. Then again, the convention I want to show you is where we have a sine of now kx minus omega t. All right. Now listen. The particle oscillator we're looking at when we began this was one that was moving in the upward x direction, upward y direction rather. And remember I told you that each particle oscillator is going to have an equal but opposite particle in that same wave system. What that means is this, that a particle that is going to, if a particle x is described, if a particle x1 is described to be here, another particle that is in that waveform that is going to have the same, and make sure you are listening to what I'm saying, waveform. Think of the ripple of a water wave, for example. So that ripple, the wave will be spread out evenly across board, right? Circularly. So if the wave is on this side, the wave on this side is going to have the same property as the wave on the opposite side of that circular ripple that is being sent out. Do you understand? A wave here is going to have the same property as one here. A wave here is going to have the same property as one here. Wave here will have the same property as one here on opposite directions. So it therefore means that I could describe similar wave that will look like this. Do you understand now? So meaning that if a wave is here, at this point here, one particle oscillator is here, the other particle oscillator in the same waveform is going to be on the opposite side. Now, so by how much are they out of phase? Let's see. They are out of phase by, if I pick this point here and I pick this point here, they are out of phase by 180 degrees. Is that clear? Now, pick your calculator and punch this in. Punch this in. Sine of 60, for example, it will give you root 3 over 2, isn't it? Sine of 60 degrees. Now, punch this in. The sine of minus 60. You will see that it is the same as the negative of sine 60. Then you will also see that this is the same as the sine. Let me write this. I said the sine of negative 60 will be the same as the negative of the sine of 60, and it will be the same as well as the sine of 60 plus 180 degrees. Quickly verify that. This will be sine of 240. You will see that it will be the same as all of this. So if that is the case, then for a particle that is out of phase by 180 degrees, we can easily designate a negative to it. Should I repeat myself? We can easily designate a negative to a particle, another wave that is moving in the opposite direction. What that means is that if I call this wave equation I've been using since y1, then another wave equation called, for example, y2 is going to look like, it's going to be negative of y1. Okay, so let's call it negative y now. Negative y is going to be the same a sine of I'm trying to prove this. A sine of is y1. A sine of omega t minus kx. I've been using minus, so I'm going to retain it. This means that if our minus comes here, divided by minus 1, y will be equal to negative sine of negative is going to be negative a sine omega t minus kx. And this guy will be the same as, you remember I said that the negative of sine 60 is the same as the sine of negative 60. So if that be the case, then we are saying that y is the same as, if I bring this minus into this place such that it opens the bracket, and when that happens, this becomes negative, this becomes positive, minus times minus plus. Hence we have a sine kx now positive and omega t now negative. So you can see that the first equation we had y1, let's call this y2. The first equation we had y1 will have the same property as a negative of y2. Should I repeat that? Our y1 will have the same property as negative of y2. Will be the same as negative of y2. What that means is that if I have a wave, one is on this side, the other will be on the opposite end here. The other particle will be on the opposite end, and we have the same property, only that it is out of phase by 180 degrees. Do you understand now? So that is why your textbooks apply these different conventions. Now, given this, let me quickly teach you how to find phase difference. So if I have a wave that looks like this, a waveform that looks like this, alright, and I call this point A, call this point B, this point C, this point D, this point E, this point F, this point G, H, I, J, and K. Maybe just L. Let's stop at L here. And I say find the phase difference between points A and F. Or I say find the phase difference between points E and G. Let's solve these two. What's the phase difference between points A and F? The first thing to look for is the wavelength. And this is the complete cycle, a wavelength. This is one wavelength here. So I'm going to use different methods, okay? The simplest is using pi's. If a wavelength is 2 pi, which is 360 degrees, then it means here is a pi. Meaning that every quarter that you have here is going to be what? Pi over 2, which is 90 degrees, isn't it? Since 2 pi is 360, yes, then a pi will be 180, and pi over 2 will be what? 90 granotes. Then if that be the case, I am saying therefore that half of that is going to be what? Pi over 4, which is 45 granotes. So if I evaluate here to pi over 4, every of these points here, they are pi over 4s. And it's the same for all waves, like that. This thing I just gave you is the same for all waves. So that's the way to solve a question like that. But now you're examining between point A and F. Point A and F, they lag by how much? So from here to here, we have pi over 4. So from here to here is already 1 pi. So that is pi plus, question 1 is going to be is going to be a pi plus a quarter, that is f, a quarter pi, that is pi over 4. And that's going to give me one whole number, 1 over 4 pi. How did I get that? This is just 1 over 4 plus 1, that's 1 over 1 over 4, which is equal to 5 over 4 pi. And a pi, 5 over 4 pi, that means it will be 5 over 4 multiplied by what? 180. 2 here, 2 here, 90. 2 here, 1, 2 here, 45. 45 times 5. Then the answer is that 45 times 5, that is 10 divided by 2, 225. Is that clear? So, they are out of phase by 225 degrees. Is that clear? The second one, which is the last one I'm solving, and I'm going to give you assignments. The second one is like this. We have between E and G. Now E is at this point here, G is here. This is very simple. If from here to here is pi, the half of it is going to be what? Pi over 2. Or just say from here to here is always pi over 4, pi over 4. So you have 2 pi over 4s. Pi over 4 occurs 2 times. Make sense? Here 1, here 2. That is pi over 2, which is what? 180 over 2, which is what? 90 granite. So it means that point E and G, they lag behind by what? Pi over 2, which is 90 degrees. Now your assignment is this. Find the phase difference between, using the same wave. Okay? Look at it, we have A here, B, C, D, E, F, G, H, I, J, K, L. Alright? So using the same wave, you are going to find the phase difference between points C and J. Point C and J. 2. Find the phase difference between points F and H. Then 3. Find the phase difference between points D and H. Points D and H. You provide the answer. Point D and L, please. Point D and L, okay? So you provide that answer in the description, in the comment section. God bless you as you subscribe to the channel. Make sure you share the video with your friends and subscribe. You can reach me out for further information on the WhatsApp number. Alright, so reach out to me if you have any other question on optics altogether. You can ask me on that platform. But also, I'm going to be releasing a one complete video on optics for both your WAEC and A level, JAM and A level. God bless you.